Professor Eager is going to be doing most day. I'll be traveling to Calgary, Canada. We were talking before we started here about the student holiday tomorrow, and the only thing I'll say to everybody is try to get ahead. You know, this is September, especially for this class. You have the ability to do these 12 hours of online lectures anytime you'd like. You don't have to wait until the live lectures are over, because I know that as soon as Halloween kicks in, you guys start having midterms and projects and a lot of things to turn in. So to the same extent, if you've already given some thoughts into what you want to do for your student presentation, you're welcome to discuss it with us after class or set a time outside of class. We emphasize at the beginning that this class is about learning, and we really want to try to make it slightly different than the other subjects. So try to take advantage of it. And there's something I'm going to ask this year is not to wait too long to get this one-page summary for the live lecture, because I can give you feedback. Last semester we had them all drop sometime in May, and then there was, you know, more than 200 pages to try to go through and no more classes to give feedback. So my plan is to set a date in October where you have to submit it, and then we'll have one more lecture to go over and have a summary. Today we'll talk about metallurgy, and I brought a few pieces of things so we all can understand what's going on. I got a video again to emphasize how we process the material from the casting. So last time we pretty much finished up talking about casting of metals from the melt going into the mold, the cooling and all that. And when we talked a little bit about injection molding of plastics, we'll go back to plastics after we're done with some of the basics here with metals. So the best way in terms of sequence is to go and talk a little bit about how steel and metals in general deform. And I'm breaking up the topic. So today we're really going to focus on metals. And when I come back, we'll do the plastics as well. What happens when you try to extrude plastics and the implications for mechanical properties. So today, metals, and then we'll bring everything in so we really have a good material overall background. So what happens specifically with metals, if you deform them, at the beginning, it's just like a rubber band. It comes back to the original position. There's no permanent deformation, really. And then there is no real consequence of loading fast, loading slowly. It's all about the atomic equilibrium. So you have these crystals and grains of steel, aluminum, titanium, and all you do really is to change the average distance between the bonds when you're in the elastic behavior. When you get to plasticity, that's where it becomes really different. You start having the migration, so the relative movement of atoms, one with respect to the other. And that's part of the reason why it's not reversible. So, and we'll go through some of those details. And we use that for forming. You know, if you take a flat plate to make the hood for a car, you really make advantage of the fact that beyond a certain point, the metal doesn't go back to the original shape. So you make you use the presses to make the shape. There's going to be a little bit of unloading when you release it from the forming, but overall you are permanently changing the shape. So just one or two slides about the elasticity, so we're all clear. There is a minimum of energy, a critical point here, where you're in equilibrium. And there's a reason I'm bringing it up here is that you see this curve. It is based on the attractive forces between the atoms and the repulsion. So you have attraction because the metals, they share the electrons together. So that's how they reduce the energy. But then the the center, the nucleus of the atom doesn't like to be next to the other. These are positive charges, so that's where you get your repulsion. So the main implication of this average energy here, it's not symmetric. So when you go and change the temperature, you're going to have a net change in the average distance of between the atoms. So let's say it's very cold temperature and everything is in this level at the equilibrium position. So this is your separation distance between the atoms. But as you raise your energy from vibration, so that's just an increase in temperature, then you oscillate at a higher approximate energy, and your center of oscillation is for a greater distance. So it's a simple explanation why metals expand with temperature. And it's relevant to, you know, even casting, if you remember when I was showing you these strips and said they deform. So what happens is upon cooling, the metal shrinks, and it's creating these side deformation and residual stresses. There are a few exceptions. So you can have a very specific chemistry that allow you to make this region almost symmetric, so you don't have a lot of thermal expansion. And there are specific applications where that is very useful. In general, ceramics have a little bit more of a symmetric peak here, so they don't have as much expansion when you heat them up. It's also, you know, a higher melting point, so your change in relative energy with temperature is less. So we've talked enough about the fact that these are springs, but one aspect with the spring is when you pull, you don't get you get an increase in volume, essentially, in the elastic portion, because there's a little bit of there is a Poisson effect, so there's a lateral shrinkage in the dimension of the specimen as you pull on it, just like a rubber band. The rubber band, though, is a little different. There's almost no change in volume, so it shrinks a lot. With a metal, you don't get as much shrinkage, so there's an expansion in the volume. And one reason I bring this up, it's specific to the elastic behavior. As soon as you turn into plasticity, so rolling, for example, and any forming operation, then your volume of metal becomes constant. So if you expand it 50%, then you get 25% change in the two other directions, and there's a conservation of volume there. So that's what we do when we do a pull test. Here, we subject a constant section of material to tension, and then as we get to the elasticity limit, so beyond this linear portion at the beginning, you have this strain hardening, and we'll go over why that's going on. And as you get to the peak is where you form a neck. So there's one very specific section in the material that's going to start reducing, and eventually it breaks. So the reason for that peak is really directly associated with the formation of the neck. And it happens when you don't have enough hardening left into the material. So let's say you have a bulk metallic glass, very, very high strain and low hardening, that it will start to neck very early on here. And the reason is when you start deforming, you may have heard of shear bending and these phenomena where the deformation localizes where it starts. So instead of redistributing to another section, it just keeps localizing and it breaks very quickly. What happens with a typical aluminum or steel, if I start deforming here, it becomes so much stronger that even though it shrank at that location, it stops deforming there, and then it's going to start deforming at another location. So it's a competition between the reduction in section and how much stronger the metal is. That's what defines this point here, and there's a bunch of equations for that. But one thing to keep in mind is there is no significance beyond this point of of the material behavior. In other words, it's not because this curve starts going down that means that intrinsically the aluminum, the steel, or the titanium, or the polymer is getting weaker. It's still getting stronger, but the net section is reducing and reducing, and that's why this plot's going down, because we define the stress here on the nominal section as opposed to the section. It would be very hard to get the section of that neck. If you were to do that, then the curve will keep going up. It's really what I'm saying. So because of the neck, it tends to fail in a cup cone behavior. And what happens there, the reason I bring it up is the failure initiates in the center typically. And that's great if you're trying to do a quality control and you want to make sure there's no effect of your surface preparation, for example, a very, very small variation. So the crack doesn't initiate on the surface, so it's not as dependent on the roughness, whether it's a polished specimen or not. You still need to have your original section to be pretty constant, so you don't artificially change the behavior of the curve. But what happens is if you run 5 samples that are from wrought product, things that were deformed by these high temperature processes, it would be very, very consistent. The different curves are going to look very, very much similar. If you send the sample, though, to different test labs and they machine it slightly differently, then you start having significant differences up to 5, sometimes even 10% difference on what they'll predict as the yield value. And that's a little bit of a problem sometimes if you're really trying to be very accurate. So when they design aircrafts, what they end up doing is they have a very big database of samples that have been sent to all sorts of different test labs, and then they'll look at over 200 tests done, what's the minimum obtained by all these labs, and then they set that more or less as being, a safe value to use for a design. So it really depends on your application, how careful you need to be on the definition of the yield. So the yield is really defined with a little bit an offset to the elastic portion. So A here is just literally a 0.2% offset, and you get to the intersection. And it's a value used a lot. And the reason is most of the time when you build something, you don't really want it to change shape. There are exceptions, but in terms of not changing shape, it means not reaching that yield point. So you put a minimum requirement for that value, and then you set it back. So it's showing here just graphically what happens over the stress strain curve, where from A to C, the amount of elongation over this distance is the same everywhere. And then you get to past the peak here, where the amount of elongation is increasing just in the center. And that's just, it's a behavior, again, that we can't really quantify. If we were to account for it, then instead of having a stress strain curve that starts going out, it will just keep going up and up. And we'll talk about that. So why is it going up? You guys know, why is it always going up? Yes? Yes. So why do we have strain hardening? You guys know? It's related to the multiplication of obstacles for the deformation. So let's go through that, and I won't show the You heard of dislocation, the word dislocation? Okay, good. So the one example they talk of dislocation is it helps because it's a linear defect. Let's say I introduce it. It's the carpet example. So I create a little bit of a fold on the carpet, and then when I propagate that fold, I'm able to make a permanent shift. So with respect to these crystals of metals, every permanent deformation does happen by shear. And instead of really pulling, on trying to pull the entire plane like this and try to overcome all the switching of the bonds, what you do is you have this little fold locally in the crystal that moves and create a small shift at the same time. And what it means, instead of trying to jump the two sets of bonds over two planes at the same time, you really are doing it over a much smaller volume of material, like 1,000 times less, 2,000 times less. Now, one thing to keep in mind is all these little things here with these linear defects, they happen within individual grains. And that was a question brought up, are all metals polycrystals? And I said 90, I didn't give a percentage, but it's somewhere around 99% of the time that you have multiple grains. So let's say that I make a few of them here, and it's something that I actually wanted to know more about when I was still a student. How is this going to work? So let's say I'm making this, and it's going to be a very thin material here. So you can do this by molecular dynamics these days and see what happens. It's pretty cool. So let's say I got this network of metal grains, and I'm trying to deform them. So every single one of them is going to, let's say I take this one, is going to have to stretch a little bit. So how is this going to really happen? It means that there's going to be shear within that grain over different planes at the same time. It's the only way to do it. If I just have one slip plane, so let's say I'm trying to deform it in this direction, like that, well, I could skew it, but I'm not going to be able to make it longer and thinner. So the only way I do that is if I have a slip in one direction and I have another slip at another location in another direction, and you need 5 slip systems active to be able to take a grain of a certain shape and just make it longer and thinner. So this looks really cool, like I've just come and try to fold it a certain way. But what if I'm trying to do that in 5 different orientations? Then what happens is there's a fold that's going to interact with the other fold. And that's very hard. So if I try to fold it this way and at the same time I try to create a fold the other way, it is a lot more energy associated with that. So the intersection of these folds creates hardening. Very early on, you have a lot of space in this crystal, especially if it was annealed, and you just go and make more and more fold as you go by, and it doesn't cause too much trouble. But there's a point where there's just so many dislocations in each grain that your yield strength is significantly higher. So why do we have more folds or dislocations over time? There's 2 principles to that. The first one is inside this grain, when I have a dislocation, what it is it's an entire loop that's offset. So let's say I take a perfect crystal and I want to make one dislocation in it. My easiest thing to do is just take an entire set of atoms and just move them a little bit here. So there's going to be a positive dislocation on one side and a negative dislocation on the other side. The volume is the same. I'm just taking an extra half plane and put it to the other side. It's not exactly how they're created, and we'll go over exactly how they're created. But what I'm emphasizing is physically, in the material, every dislocation is not just unidirectional, it's an entire loop that closes back on itself. So if I want this loop to create certain deformation, I'm trying to move it in different direction. So I'm trying to move this loop as opposed to a fold. It's a loop. And there's other loops that are traveling in other planes. So when they intersect, they will pin each other. So let's say, for example, right here, and there's no specific location for this location to be. It doesn't have to be just in one slip system. So it can be going down this way and then turning around. So the section that's turning around is the one that you see on step 1. And the reason it's pinned is, let's say it's coming on a slip plane that's essentially perpendicular to the surface. So no movement in that plane. And then there's a good 45-degree orientation. That's our level 1 that's just expanding. It's expanding to the point where you just have the two sides touching, and then it's popping another bubble. So we call these Frank Reed sources. They have other names, but the very principle here is just by deforming the material, you start to multiply these dislocations, and this is one of the main mechanisms. So this is really where the hardening comes in. And it's about as complex as we can go, unless you have questions. We see a little bit here when I was talking about the loop, how it works, where they have some different nomenclature for the place where you have this half plane that's extra on the other side. So if you have an extra half plane on top here, and on the other side you have the extra half plane at the bottom. And it really is, after 25 years of dealing with this, all I can think that you need to know that they are there, and their main implication is that you can anneal them. So when you heat up and you soften the steel or the aluminum, what happens is you get them to recombine, and you decrease your density, essentially, because it's all thermally activated here. These things don't stay exactly in place. They always move a little bit because there's very little energy involved in moving one of them. What you do is, along the length, you just jump one atom at the time. You can literally come here and say, hey, why don't you move over there? And then you do them one at a time, as opposed to trying to do an entire plane at the same time. So it's even more clever than the fold that we were talking about, because you just do one piece at a time. That's why it's low energy. It's low energy to move them, but it's high energy when one tries to go over the other. And that's the point where they become stationary and lead to this multiplication in a certain plane when it's locked in the other plane. All right, so let's go back to reality. I brought some samples where they were subjected to different heat treatment. And I could, but I don't think we need to go through all the details right now. The reason I'm going to circulate it is you'll see specifically on the 2 copper samples. So they laid out this way. You have a brass alloy, and you can see when it's annealed at the higher temperature, there's a certain texture in the area that it's deformed. So this is the reference surface. It's very, very flat. But as a result of the deformation, it became rough. On the copper, it's the same. So you have a reference material. You have different temperatures of heat treatment, and you'll see it's the one in the center that has what we call an orange peel effect. It's very rough. And it's a signature, essentially, of those grains that we just talked about. So if normally when you're talking about a beam, you don't really see an effect of individual grains when you're deforming it. There will be special cases like deformation of silicon. wafers and things like that. It's so few grains, if it's not just one through the thickness, that their individual behavior does matter. And on these samples at the intermediate temperature, it's the same. The grains are so big, almost through the thickness of the sample, that you see the roughness. So part of the reason for the roughness is some grains are going to be oriented in a way that it's easier to deform them than others. If you have, say, 5 or 10 of them through the thickness, they all have to do more or less the same thing and follow a very nominal deformation behavior. But if there's a free surface, that's where you can have a piece of rock or something hard like nuts in a piece of bread that are just not moving, and everything around it is going to move. And that's what leads to that roughness. So 2 levels, really. If we try to summarize this, maybe 3. So at the very fundamental level, we do have our atoms. And we've talked about them in the sense that they want a certain distance between them. Fine. All right. So there's essentially a certain radial distance between the nuclei, the atoms, that you want to respect. Not too bad. That's what leads to the elasticity. Then if you go to the higher level, you will have vacancies in this crystal. And these are just little holes that move around all the time. And they don't matter too much for us with respect to deformation. They're going to affect diffusion and other things that are going on. But the main thing that I want to emphasize here are these dislocations. And the implication of the dislocation is that's how you get, so the R gets you the spring effect. And the dislocation, they give you the shear. That's how you end up deforming, really. And the grains, they are the higher level, and they give you really the elongation on a macro scale, or the change in shape, I should say, by compatibility between them. So when we're trying to make use of this for forming materials, what happens is it's important to think that there's going to be a point where you have enough dislocation. It's saturated. And I have some examples here on the next slide. These are more neat than what they would be in a simple deformation. So let's try to see what happens to our real stress strain curve when we have this. So on the true stress behavior and strain, you have your elastic behavior, you start deforming, this is your neck point, you keep going and going and going, and you get to a point where really there's not a whole lot more hardening anymore. And just for reference, this would be something of the order of 100 to 300% strain. So the material is between 2 and 3 times longer than it was, maybe a little more. It really depends on the condition. It's even at ambient temperature. And that reason is you're at a point where there's so many dislocation that even at ambient temperature, they will recombine and you can't have any more. So your hardening behavior is essentially saturated. So the reason for the saturation at this point is just having a structure where you have these walls. So we call them cells. So inside the grain, so within this guy, you have regions that are good sites for recombination of different dislocations. Does it matter? Well, it matters in the sense that you can see where you would want to do your deformation processing at high temperature. So you get to a certain temperature where what you would like is a constant yield strength. It's a lot easier to analyze where you just keep deforming and it's the same strength all the time. And that's a lot of what's happening in the hot forming process. And that's pretty much our next steps. These are actual grains, and the reason you have these little bars in this case is we have twin formation. Just a little bit of variation of the crystal orientation within each grain. It's specific to copper, but it's an example where you can see the boundaries. So you got one grain right here, another right here, you got another here. So they're relatively well defined. You have one here. So the scale, 200 micrometers. So these are relatively big grains. It's one of those samples there. Yes?
One thing we think about a lot with silicon is precipitation of impurities at grain boundaries.
Mm-hmm.
But that's because of electronic property. But I guess you could also have dislocation loops because of big precipitates that form. Is that something you think about with metals?
Okay, so the question was about what happens with the grain boundary and the dislocation and the precipitates for metals.
Right, for different impurities you'll have.
Yeah, so if you can get your dislocation to reach the grain boundary, it can essentially heal itself there. It can disappear. The reality and the reason your question is good is one dislocation physically in the grain is going to be pretty small on a normal grain. So if, say, this is 100 micrometers for metals, even if you put 10 micrometers, they are relatively small, and therefore they can't get to the boundary easily. But with silicon, these dislocations are much more rigid and bigger, and therefore it is a mechanism, I'm sure, where they essentially really nucleate on one grain boundary and go across the grain in certain condition if it's a small enough grains. And your grain size becomes important on determining whether you form the dislocations. The situation with the impurities and the condition of the grain boundary is just an additional factor, and let's not get too much into that. But what I like about the example is even with nano-crystalline metals, so here these grains are on the nanometer scale, what happens is, let's say now your grain is this big, and your original dislocation used to be about the same size. So now you almost have no dislocation inside the nano grain, and you'll need a dislocation to be nucleated on one side and go across to get your deformation. So and that's a reason why these nano grain material, your hardness keeps going up. So this is a reduction in grain size up to the point where you reach to about, I think it's 10 nanometers or so, and then your yield strength starts to stabilize beyond that. So it all relates together. And believe me, I'm throwing a lot of information here. You don't need to try to remember it all. You guys have different levels, so go. If all you come back home with is, oh yeah, the reason we have strain hardening is the interaction between the dislocations, that's great. If you want to remember a little bit more what we discussed, it's all a question of relative scale between the dislocation and the specific material that you're dealing with that defines how it's going to interact together. Okay. Now it's time for the fun. I should show the video. Let's see. So what's going on here is they feed a cold plate of steel into this oven to heat it up so it becomes red and essentially softer. And then it goes to this different stages of rolling operation. In this case, they're making a beam. And the reason to have it, there are a number of reasons to have it hot. The first one is you're reducing the load that you need, but also you don't have as much hardening. So we're not into this range here where the material is really into, close to breaking. When you reduce the yield strain, it means that you don't have as much of an elastic stress, and you have a very good cohesion in the material. The other aspect is allows to blend in all the chemical content. So you homogenize your surface, except that the surface here is getting oxidized constantly. And that's the mill scale that I mentioned a couple times. And these mills traditionally, or maybe even right now in Korea, China, India, everywhere that you make a large quantity of steel today, you have to be careful with condensation and other things, because when the steel is so hot, if you drop a piece of, even drops or a small flow of liquid on it from a cooling unit or anything like that in the factory, it's going to locally quench the steel and leads to a permanent change in the behavior. They call these hot spots. So there's a lot of ways you can do it, and you see it moving sometime where it will go, well, that's a nice beam. Okay, so the idea here is keep it hot so you are not having to drive tremendous forces. If you try to do these shapes at a lower temperature, the roller, they bend. There's so many things that don't work for you. You cannot have as much of a reduction each pass. It's not practical. So most complex shapes are done at high temperature, and it's has a lot of implication with respect to the grains. So this is something I showed on the first class, and we started talking about, and we came a little bit, I think we were sort of getting a little too far for the information we had. So it speaks to what happens if you do it cold. So these samples here, they were cold form first. So there was an operation to make this plate very consistent in thickness. So it's an ambient temperature, cold forming operation, and it leads to a much straighter product. So if you need to build something that's with starting very, very straight sheets of metal, a lot of times you want them cold formed, because if they hot form, when they cool down, they don't have the same dimension control. So what happens when you cold form it, you see the little hatch into the grains. This means you have a lot of dislocation. So you squeeze the grains just like this one, and it has a lot of dislocation in it. So the regular process when you start in this condition, so the grain is originally, so let's say here the grain is just very square, everything is cool, and you deform it 200%. That same grain now just looks like this. It's got all these dislocations. It's very high energy because you have more boundaries, grain boundaries, and you have more dislocation inside of it. So what ends up happening here is, instead of trying to heal this microstructure, you just start forming new grains in it. So you start at the grain boundary, typically a triple junction, forming this new crystal by taking over, by diffusion, taking anything you like, and you buying in the material that has all the dislocation in its strain, and that's the recrystallization. So you see these smaller grains there. And then eventually these grains will grow just by eating up the grain boundaries from the others. It's a very typical process, this recrystallization. And what you like to do in the hot forming is to be in a regime where it's constantly happening. So there's a certain amount of deformation, all of a sudden your dislocation are increasing locally. Oh, you have a recrystallization, and it balances out. So that's why as you keep deforming, depending on the material you have, you can go through a peak of stress, but eventually it becomes constant. And that's a lot easier to deal with in process control. It gives you a very nice homogeneous microstructure. In the end, there's just so much going on, so many movement and diffusion, the remaking of grains all the time, that it'd be very, very hard not to have an homogeneous microstructure when you're done with this process. So you feel you know why we do this hot? Sure. The typical microstructure you'll get are micrometer size grains. So when we were talking about making this nano, it doesn't happen easily. And that's why a lot of the specialty or advanced material have to be made by electrodeposition or other processes, because the smallest that I know of you can make here are like 100 micrometer grains or something like that, or maybe 200 nanometers. There is just a limit where they will just keep recrystallizing if you're doing it by deformation and trying to refine it beyond a certain point. The example of silicon, if you heat it up, you could do other things with silicon as well. Essentially, get these grains to grow and behavior becomes very different. Okay, well, you don't do that all the time. So I'm already moving on to what happens a lot of times is you forming a piece. Let's say the pipes are, it's because that's something I'm working on a lot. You start with the plate that has been made by this hot rolling process, and it'd be very hard as far as a continuous process. If you can't do an extrusion, for example, it's very hard to try to make this into a pipe shape with a hole in it. So when you do that, you have to do it in sections or by extrusion. So for cost reason, a lot of times what they'll do is they'll take that plate and gradually form it, and a lot of time it is done cold. So you make it into a circular shape, and you weld that seam right here. You, by different processes they're used today, depending on the thickness that you have. But one consequence of just doing this process of going from the plate into this shape, if you're doing it at ambient temperature, it means that your surface is getting harder. You have this deformation of the plate as you're forming it, and it happens even if you're forming an airplane wing component, a double curvature component. If it was done by stamping, you have a big gradient through the thickness. It's not how it's done for aerospace, and we'll get to that. But for now, let's just assume it's the easiest way. You take the stock that's out there, you bend it, and you put a welded seam on it. So if we take a section of that wall and do the hardness test, that's what I'm showing here, you see that there's a higher hardness on each side. So let's say we say, here's our ID, and here's our OD. So our yield strength is going to look like this, a little plateau in the center, and then it goes back up. So why is that going on? The reason you have the plateau in the center, and this is something we've done by finite element analysis, the blue is you remaining elastic in that section of the material. So over here, there is no permanent deformation. Here, it was essentially compressed, so you have a negative strain. And then here you had a positive strain, which has the same effect of creating increased density of dislocation. So why did that matter? That it matters for a couple things. First of all, if I do this process and I bend it over and then I weld, when you cut those pipes, they bounce back. You'll have, let's say this is about this size, you get a gap here that could be half an inch. Okay, so what does that mean? It means that they have stresses on them even without any load on the outside. So you have this residual tension on the external surface, and unfortunately that's the reason why when they use underground, even if the pressure is not too high, sometimes they have what we call stress corrosion cracking in the interaction with the environment. There's a little bit of penetration of moisture under the coating of the pipe, and then all of a sudden you start forming cracks here on the outside. And you wouldn't if after forming this pipe it had been normalized, for example. Just heat it all up to get rid of this, not only the hardening gradient, but mostly the residual stresses is what is the problem for this particular case. But I bring this example because if you don't know how the pipe is made, then there's a lot of things you can't predict on whether it's going to be a problem for different kinds of services. So there's a typical approach if you are in the pressure vessel industry and if you can afford it, you go with a seamless pipe. So these are made in sections. They're more expensive. We'll go over how they're made. And you get rid of having a different chemistry from welding here. You avoid having these effect of different strains and residual stresses all together, but it's a lot more expensive. So the counter side of this, if you just ask for a pipe, I think that if you tell me I want a 12-inch pipe, this is the one I'm going to want to give you, unless you are very, very, very specific that you don't want it, that you want something different. So it just speaks to, as engineers, trying to know enough when it's important. It's not a lot of times these things don't matter. It's okay to have residual stresses if it's a pipe in a formation for a building and low strength steel and stuff like that. But there's a lot of conditions where after the fact, in terms of the long-term performance, the processing that just plays a big role. Yes?
Would it be feasible to cast a pipe?
Yes. So that's, I think, the second lecture. You'll do it with cast iron, the ductile iron. And what it allows you is not only you make a pipe, but you can make the fittings that go in the end of it. So it's great. It doesn't give you very high strength. It can give you something that's very brittle. So you have two choices. You can make it strong, very brittle, typically not the case, or you make it very, very soft and ductile at the same time. So it's used for water service a lot, yes. It's got good corrosion resistance if it's cast iron. Typically pretty thick wall, though. If there's going to be a limit on how thin you can be, there's not a whole lot of dimension tolerance that you can do. The surfaces are pretty rough. So we're looking at, 1/4 inch to plus thickness. You can also make these and then draw them and adjust them so you get a better behavior after the fact. So, and they would, some of them will still be called seamless if you deform it enough after the fact that you're losing the history of making that well. Very good question. Thank you. All right, guys. Time to go.